for a little bit over 2 years. Done some really nice work on detector development. I guess we'll hear about it a little bit more today. He apparently has had enough of me and is ready to leave. So
Thanks for the introduction, Dr. Yang. So my name is David Rinaldi. My work and my thesis is entitled Radiation Detection Using a Semiconducting Nanocrystal Detector. And I'm just going to get right into it here. So the overview today, I'm going to give a brief introduction to radiation detection, an introduction to nanocrystals, some of their theoretical models, some of their emerging properties. I'm going to talk about the choice of lead selenide, the specific nanocrystal used in the study. We're going to take a look at some computational simulations, take a look back at previous work and some of the challenges of that work. And then we're going to move to sort of a part two, sort of what I've done here at Oregon State, including the nanocrystal synthesis, the detector fabrication, the results of the synthesis, the results of the fabrication. I'm going to wrap it up with some conclusions, and then I'm going to look to some future considerations. So some of this may be review for a lot of you in the room, but I'm just going to go over how radiation detection works in general. So we have some ionizing radiation interacting with the detector medium, ultimately producing charge carriers. So these charge carriers can be produced in the material, in the detector medium itself, such as gas or with semiconducting material, or for example, with scintillation medium, the light will scintillate and then get converted to charge through an auxiliary piece of equipment, such as a photomultiplier tube or a photodiode. But charge carriers will be created, and then they go through an electronic system. It usually consists of a preamp, an amplifier, a single-channel analyzer, multi-channel analyzer, or a preamp and FPGA. And then the output of the electronic system is what we as people use to sort of infer things about this ionizing radiation, so maybe total counts or an energy spectrum. And ultimately, we really want to make this a very efficient process, this ionizing radiation to charge carriers, and we want as more charge carriers in general, the more information we could glean into the ionizing radiation that has impinged onto the detector. So what would an ideal detector look like? Well, here are some attributes that I consider to be an ideal detector. One, low cost. Makes sense, I hope. Two, variable size. So you want something you might be able to have in a portable device, or maybe something large for shipping containers. Also, you want high efficiency and high resolution. You want to stop high energy gamma rays, and the high resolution. You want to have confidence when you're trying to characterize and identify different radioisotopes, different radionuclides. So currently, gas detectors, low cost. This one back there is the ionization chamber and a smoke detector. So this is very cheap, but not too variable in size. You have to worry about recombination. You have to get high voltages when you want to make gas a little bit bigger. And so high efficiency, gas just doesn't have it, just due to the densities. Scintillation detectors, however, variable size, usually for portal monitoring. So you could have large surface area scintillation detectors, some plastic, you can get pretty big sizes. And the resolution, not too shabby. But really the good resolutions with the semiconductors, very, very high resolution. The variable size, the crystals can only be made so large, and they are certainly the most costly of the radiation detecting devices. So let's see, can nanocrystals, can they have all three attributes? Can they be this ideal detector? Some academics say that nanostructured materials will be the future of radiation detection, but in essence, probably far into the future. So what are nanocrystals? So some of you may have heard of quantum dots, essentially nanocrystals. So let's take apart that word, nanocrystals. So nano, the prefix, a billionth, very, very small. We're looking at 10 to 10,000 atoms per nanocrystal. Sizes range from about 2 nanometers to 10 nanometers. Although this is not a hard and fast rule, you could have things on either side, still call them nanocrystals. The crystal, repeating crystalline structure, this is a TEM image. We can actually see the atomic planes as a crystalline structure from the TEM image. And something I call superior physics. So they have a discrete electronic and optical spectrum due to quantum mechanics, and we'll talk about this. But essentially, the thing to take away is more charge created, less heat emitted. So we have more efficient materials. And that's sort of what this cartoon is depicting. These phonons are essentially sort of a heat loss, and instead of this heat loss, we're getting more charges being created. And we're going to definitely talk about this later on. So theoretical models. This was the hardest part of my research. It's very hard for me to wrap my head around some of the quantum mechanics that came up. But complete electronic and optical states are very difficult to model. Many assumptions must be made. I could talk about the K.P method. I could talk about the effective mass approximation. But I think a team at the University of Rochester, in collaboration with the team in France, said it the best when they said, lead selenide nanocrystals exhibit a series of well-defined and widely spaced peaks in their absorption spectra, but despite this apparent simplicity, prominent spectral features are observed that appear to completely violate basic quantum mechanical principles, and in fact, lead selenide nanocrystals have proven to be a very complex materials for which a general understanding of even the most basic characterizations has remained controversial. So I'm not the only one who has a hard time wrapping my head around this stuff. However, there is something that we can turn to that will give us a good intuitive understanding about nanocrystals and sort of how these things work, how these really interesting phenomenon emerges from them. That's the particle in a box model. It's usually an introductory to quantum mechanics problem, and the results are a discretization we'll talk about. So the particle, we could assume it to be the electron, which is more like a wave in this case than a particle. And the box we could assume to be the nanocrystal. So just me setting the stage here. There's a lot of math. If you guys have questions about this, I'm more than welcome to talk about this afterwards. So I'm just going to breeze through the math here. What's really important, and the takeaway here, is the discrete solutions. And these are sort of depicted here, n equals 1, 2, 3, 4. And so we have discrete solutions when we apply some of these boundary conditions. And what else is very important is that the energies are also discrete. And they vary 1 over L squared, where L is sort of the dimensions of the box. If they're all the same, if it's a cube, they're all equal. It turns out in the lab that the energy varies more like 1 over L, not 1 over L squared. More rigorous calculations also show this. Experimental curve fitting shows this as well. But in general, if we just look at this, if we make this box smaller, we're going to have higher energies. And in the lab, if we make these nanocrystals smaller, the bandgap energies also are widened. They're larger bandgap energies. If we make this nanocrystal smaller, the optical absorption and emission spectra also shifts to higher frequencies. So we could sort of get an idea about how these things work, at least some idea with this particle in a box model. So how do we know if we're when can we apply that model? So I need to talk a little bit about the Bohr radii. I'm not going to completely bore you with the derivation, but it essentially involves setting the Coulomb force between the electron and the proton equal to the centripetal force. So this was modeling the hydrogen atom, has a very rich history. The electron sort of orbits the proton like a planetary body. But ultimately what we get is this Bohr radii, and it gives us an idea sort of about the size of the hydrogen atom via these useful fundamental constants. But I'd like to, and these constants, let me just talk about it a little bit. So this is A sub e, which is the Bohr radii of the electron, 4 pi times this optical frequency dielectric constant evaluated at infinity times the reduced Planck's constant squared all over the effective mass of the electron times the elementary charge squared. And it gives us, it's a useful metric. It's a useful metric for us to talk about quantum confinement. So I'm going to tie all of these things in together hopefully very soon. So Bohr radii, we could have them for holes, we could have them for electrons. The effective mass changes. You could also have them for excitons. Those who don't know, it's sort of a quasi-particle. It's not a real thing. It's actually an electron-hole pair. We could talk about this as if it's its own particle in itself. So if R is the defining confining dimension. So in our case, it'd be the radius of the nanocrystal. And if we take, we look at this ratio, we have the confining radius over this Bohr exciton radius. And if this is a low ratio, if this is a low number, that means we're in a strong quantum confinement regime. And if we're in a strong quantum confinement regime, we can use the particle in a box model, and we could get these discrete solutions. So it's all about trying to make this a very small number, so we could either make the nanocrystal small, or we could hope that we could have a Bohr exciton radius which is very large, and it's material dependent. So different materials will have different Bohr exciton radii. So we get some different regimes. We have weak confinement when the radius is much larger than the radii, the Bohr radii. If the Bohr radii of the electron is larger than the Bohr radius, then the electron will be in that particle in a box model. The hole won't be. But if the Bohr radius of the hole, the Bohr radius of the electron is larger than this confining dimension, this radius, then we're in a strong confinement regime. And that's when all these really cool things start to emerge, these really cool emergent properties. I'm going to talk about these emergent properties in quantum confinement. So we have a discrete band structure resembling that of molecules or atoms. So over here, this is a density of states. And over here in a bulk semiconductor, and sort of classical things that we work with, classical semiconductors at least, we have a continuum of energy states for which an electron can populate. But if we start moving over here to quantum dots, quantum confinement sort of takes over, and we get this dispersed, sort of quantized, this discrete electronic states. And they resemble a molecule or atom. In fact, nanocrystals or quantum dots are referred to as artificial atoms. I thought that's kind of a cool name for them. And so we get some pretty interesting things when we discretize their electronic states. One thing is that size-dependent band gap I was talking about. So we have some nanostructures here, and we see once we make them up to a certain length, we see that the band gap starts to increase, and we could actually use size selection techniques, and we could get a material. If we size select, we can engineer the band gap essentially, which is a very cool thing. Following from this, these are all sort of tied together. In fact, they're all cadmium selenide. We have well-defined optical and optical absorption emission energies. Really follows from some of this stuff. And so what you see here is you may have seen these quantum dots, and these are used in as biological markers, and they're also used for scintillation material. Because if you can engineer your emission energies of your photon, you can link it up well with your PMT or your photodiode. So there's a lot of research for scintillation material there. The big thing, though, is carrier multiplication. So one photon can create multiple charge carriers instead of losing excess energy to heat. And so this is what we see over here. Let's say there was an electron in the valence band. It raised 2 energy band gaps. Now the electron is in this excited state. And so it's going to relax. And instead of that energy being emitted as these phonons, these lattice vibrations, that energy will now be used instead to create another exciton. And this is impact ionization. So essentially, you're getting 2 for 1 with your photon. You're getting, instead of having that extra heat, you're getting more charge carriers, and that's good for radiation detection. That's what we want. The opposite of this process, Auger recombination, we have an electron here, and it's going to combine with a hole. And again, instead of that excess energy being emitted as heat, it gives this energy to an existing exciton. It excites an existing exciton instead of giving off as heat. And the reason why this isn't as efficient as it usually is in classical material is due to that discretization of energy states. So the energy states are very far apart. It could be that if this electron wants to relax, it would have to simultaneously emit multiple phonons. And the simultaneous emission of multiple phonons is not as likely an occurrence as if it were smaller energy states. So it's because of this discretization, that you have increased exciton-exciton interactions, and that's what this is depicting. You see this electron relaxing, and you have multiple charge carriers being created. And ultimately, what this comes down to, what we see, or what we hope to see, is a difference in a bulk material. So in this graph right here, sort of this y-axis, is the energy needed to produce an electron-hole pair. Sort of the W factor, sort of the average energy needed. And over here on the x-axis, we have the energy of the band gap, which is the theoretical minimum energy that you would need to create sort of these electron hole pairs. And so this line, W equals Eg, represents sort of a perfect conversion of energy into electron hole pairs. And as we see, most modern materials, they're not close to that line. And so we hope that carrier multiplication, more efficient physics, the superior physics I was talking about, will bring these new nanocrystal materials closer to this W equals Eg line. So the choice of lead selenide. So lead selenide exhibits a very strong confinement due to that large exciton Bohr radius I was talking about, sort of this R over AB. So we'll talk about classes of semiconductors. Over here we have 2,6 cadmium selenide and cadmium sulfide. These are the pretty popular ones. 2,6 because cadmium's in group 12, We have selenide in group 16, so we have 2,6. But if we move over and we get lead from group 14, we get these 4,6 semiconductors that you see here. And we see sort of an explosion of the Bohr exciton radius. And so we get stronger confinement. So that large number on the denominator leads to an overall smaller ratio, leading to that stronger confinement regime that I'm talking about. So it's well studied. Operate at room temperature. There's a low temperature dependence on the band gap. So it's sort of this figure that I have here. We'll establish synthesis methods in relation to other nanocrystals. We have a tunable band gap I was talking about. So we do size selection. We can get, if we want 0.7, we could do that. And promising results from detectors in previous work. And so there have been some previous work, most notably at the University of Michigan, Dr. Ji-Hung Kim. He was working under Dr. Mark Hamig, and they made some really interesting detectors, and they made some really interesting results, and I'm gonna touch on that. I thought this was very cool. So it's computational models and density functional theory. So they take these really from the ground up, atom by atom, and they sort of tweak all the interesting parameters. So 2.1 nanometers was the largest diameter. They used lead selenide due to computational limitations. Unfortunately, they weren't able to expand to larger sizes. They found that the shape of the nanocrystal is more important than the size. Again, you have to take that into consideration within the study in regards to transport, and that's what they really look at. They tweak many parameters, and they look for the best charge transport. They rotate different faces towards each other. They move them distances from each other, and they see what's best, what might be the best configuration. So might look to the future, might look to these people for the future. This was at Cornell University when we really get better control over these materials at these type of length scales. So I did a simulation myself as well. I was just curious to see if the alpha particles were going to get stopped and deposit their energy within a detector that I could make. So I made a sphere of air, made a right circular cylinder with half lead, half selenide. And so I just wanted to see, I directioned them upwards, 5.3 MeV. And we see at 1 millimeter, it qualitatively stops a lot of the alpha particles. Even at 1/10 of a millimeter, it stops a lot of the alpha particles. So I was pretty convinced that the alpha particles were going to get stopped and deposit their energy in the detector. So the previous work, let's take a look at this graph. It's a pretty impressive graph. We see that the previous work by Dr. Ji-Hung Kim from before, they were actually able to get comparable resolution to some of the top detectors, some of the state-of-the-art detectors that we now have. And this is really amazing, and I can't stress that enough. But unfortunately, these are the type of materials that they were creating. And so they're also only hundreds of micrometers thick. And so some of the challenges is we want increased thicknesses. We want things that don't look like brittle solids that have trap sites for charge carriers. I think some of the pictures sort of encapsulate. So this is not the best type of material, not the best for extracting charge. So I guess the question is, if hundreds of micrometers work, what I wanted to look at is, can we push this to the millimeter scale? And so that's what I was looking to do within this work. And so how did I do that? So in a glove box, get a 2-neck flask, put 0.65 grams of lead, 8 milliliters of top, 1.5 milliliters of OA, oleic acid, and 2 milliliters of DPE, which started to solidify on us about halfway through our batches. I guess something changed with the air conditioning system, but it started to freeze on us, and that wasn't fun. So we heat that for 1 hour at 90 degrees. We degas it through a Schlink line, set up to a vacuum mode, and then you're supposed to let this mixture cool to room temperatures. However, once we did that, the lead started to solidify on us, and that was a problem. So to sort of combat these two problems of liquid solidifying on us, we used a digital thermometer, we used an extra oil bath, and we try to keep these solutions in a liquid state. And so while we're doing that degassing, you want to make 1 molar of top SE, put 0.131 grams of selenium, mix with 1.7 milliliters of top, shake that up, add it to the previous solution, and then what you're going to do is you're going to heat 10 milliliters of DPE up to about 150 degrees, and you're going to inject that mixture of the two solutions into your 3-neck flask. And once you do that, the temperature will rapidly drop, probably from 155 maybe to about 110, 120, around that area. Your concentration of precursors will also drop as they begin to start to nucleate and start creating those crystals. Then we'll go to the Oswald ripening phase, and at about 6 minutes, we'll take them out and cool them in cold water. And so that's what we see here. We have a hot plate here with a magnetic field. We have an oil bath with magnetic stirrers agitating from that magnetic field, stirring and making a more uniform oil. We also have some magnetic stirrers within the solution itself, sort of helping that reaction go through. 155, I always inject it at 150. This is just a photo opportunity. And so we have some argon coming in, and we're doing the hot injection process. So this is the hot injection method. Again, once we're done, we let it cool down in cold water, but we are not done then. We still have to clean up. So aqua regia was used, very strong acid, to get rid of a lot of the metals. So we have 1 part nitric acid, a 3-part hydrochloric acid. Rinse out all the glassware with that, rinse it out with deionized water, set it in the oven to dry. The entire process took about 3 hours at first, but then we got used to things. We streamlined it to about 2 hours. Over 15 batches made. I have sort of a little Excel sheet here. It would have more if there wasn't a hard drive failure. Happened about a week ago. Was not much fun. Luckily, a lot of these batches were made under the same conditions, the same injection temperature, the same growth time, the same chemical ratios. Okay, so now you're done cleaning up your glassware. You have to clean up your nanocrystals. So to remove any unreacted solvents and precursors, you take the nanocrystals, you put ethanol in, which is a polar solvent, and then you centrifuge that for about 3,000 rotations per minute for about a minute. Then you decant the supernatant, which just means you get rid of the excess garbage, essentially. Put more ethanol, repeat the process, and you'll do that until you're just left with nanocrystals and ethanol. At this point, decant the ethanol, and we're going to mix that with a nonpolar solvent, chloroform, and set some aside for some absorption testing. So what are you left with? Not just nanocrystals, actually. You're left with nanocrystals with capping ligands. So capping ligands provide stabilization during the synthesis process, and you can create exotic shapes with this. So if, they preferably may bind to certain facets, and then others might be able to grow. And that's how you get these cool sort of nanostars, many other different types of exotic shapes that you can make. So these ligands I'm talking about, these oleic acid ligands, 1.5 nanometers, that is actually relatively large on these scales, especially for charge transport. And unfortunately, they're insulating. And so that's not a good thing. Over here, this is sort of a cartoon picture. This is actually lead sulfide, and they're OA and OH ligands, but it still has the same rock salt crystal structure. And so this is a good idea. It's pretty well scaled. So to combat these insulating ligands, there are a few methods used. So there's some ligand exchange methods where you try to wash some of these off and put some other ones on there, better conducting, shorter ones like EDT or hydrazine. Another one is composite blending, where you take a conductive polymer, such as MEHPPV, sort of mix it in with your nanocrystals, and hope that that conductive polymer can help you take charge and extract it throughout the uniform solid. I'm not going to attempt to talk about how you say MEHPPV. And that's what we used in this research. Either 30 or 60 milligrams were put into 2 milliliters of chloroform. So results of the synthesis. These images were used. We had a TEM microscope here at OSU, the Titan, and this is very validating to see that you've actually made nanocrystals, and size distribution anywhere from 7 to 12 nanometers in diameter. Unfortunately, we weren't able to do this after every single batch that was made. It's a very expensive process, but at least for one batch, we see that we have correctly synthesized nanocrystals that we wanted. So we did what we set out to do in that sense. So once you have the nanocrystals, you want to make a solid out of them. So it goes from a liquid to a solid at this stage, which is the deposition stage. So we used a 25 microliter pipette. I had some help from my undergraduate research assistant, Ms. Nancy Sina. This process was the most costly time component. You have to do this drop by drop, let the solvent evaporate, let the chloroform leave, and you're left with a cracked, thin layer, which you essentially stack layer and layer on top of. It's not really, in my opinion, the best ways of doing things, but this is what we're doing. Furthermore, I want to thank my girlfriend for letting me use her hairdryer. It's helped greatly speed up the process. As you see, I'm taking a sort of a measurement there, and it's helping dry, it's heating up. If you were about oxidation, that DFT report that I looked at, I found this. Exposure to air is thought to remove ligands from certain NC facets and improve charge transfer in certain directions. So we had that going for us. That was pretty interesting. So once you make your solid, you want to put some electrodes on. This is the gold evaporation machine. Over here we have a tungsten boat, and that's where we put the gold. We have a sort of a plate up here that we put the detectors on top of. I changed that so we can place multiple detectors and coat multiple detectors at the same time. You throw this sort of glass dome on the top, and you go down to low vacuum, sort of 10 to the minus 5 torr. You place about 78 amperes of current through this tungsten boat, and that will make it hot enough for the gold to essentially evaporate and coat the surface on what you want it to coat for. But unfortunately, we needed large amounts of gold. It didn't adhere well to the PLA plastic, what I'll talk about, nor the NC surface itself. The machine itself didn't seem to work well, and even if it were to work well, which it didn't, it's still necessary to attach something physically to the gold. And that sort of introduces noise. Unfortunately, it turned out to be a resource sink. Money, energy, and unfortunately time being the most valuable resource in this experiment. You have to schedule time on this machine, so it took up some time. So there are other electrodes, soldering and epoxy. So soldering onto the nanocrystals was sort of a futile effort. At least I couldn't get it to work. Some Class C detectors, and I'll talk about what those are. We were able to employ sort of soldering methods, but I believe it actually the solder and the PLA plastic, I believe, mixed together, and that's why it seemed to work. Although there's a physical boundary in actually touching the nanocrystal, and that's how charge, I believe, was extracted. The best thing, though, was really the silver-based conducting epoxy that we got from Thor Labs. That was the best way, the simplest way to make those electrode connections. So I made a couple of different detectors, and I labeled them all in sort of classes of prototypes. So the Class A prototype, sort of just starting out, not really knew what I was doing. Really, there was no containment for the liquid, so we got this low-quality detectors where the liquid just kind of went everywhere. None made it to testing, although this was the best gold that we were able to get in the entire project. So moving on, trying to combat that, Class B prototype solved this problem by structurally confining the nanocrystals within this PLA housing. And so you see this one went into gold deposition. We put a lot of gold in. Unfortunately, we're not able to make that steady electrical connection. So what we did was we put some high-grade aluminum, and then later on even aluminum foil. But even these were hard to make a connection to, unfortunately. So unfortunately, none of the B detectors were able to proceed to any sort of testing. Third time is the charm. We have the C-class prototypes. So it's a mixture of A and B prototypes. So we used copper and aluminum on the bottom, which was very easy to solder onto. And then we used this type of housing to sort of structurally confine the nanocrystal liquid as it dried. And so we superglued that to either one of the bottom metal contacts. Some Class C detectors were blended with 60 milligrams of that conducting polymer I talked about. And so we used epoxy for some of the electrical connections and solder for some of the others. And so here are some IV curves from these Class C detectors. And unfortunately, we had an ohmic. These are ohmic, so a linear relationship between the voltage and the current, and that actually swamped out radiation pulses. It's not the curves that we were hoping to expect, not semiconductor curves, which have very low voltages very low current at low voltages. We had this ohmic-like plot. MEHPPV was not so much a factor. The difference between these curves and these curves were actually just the metal on the bottom. So these are the copper, and these are the aluminum bottom contacts. We have some similar curves in previous work. These are both the drop cast. But if you spin cast, apparently you can get better types of material. You can get more of like the semiconducting curves that you want. And our scales are a little bit different too. He was able to achieve much lower leakage currents. And you really want low leakage currents because you don't want to swamp out the radiation pulses within your detector. I believe Noel said about 10 to the 9. You don't want anything more than nanoamps coming out. Although this does show that perhaps our electrodes do work. We also did some absorption testing. So you're able to infer some things about the size distribution and the size of your nanoparticles with absorption testing. So here's a sample of some nanocrystals and a little bit of chloroform. I made some dark concentrated samples, so more chloroform, and some light samples with a little bit, the diluted samples had more chloroform in them. course. So we used the Carry 5 spectrophotometer, and the physics department was nice enough to let us use their spectrophotometer. And so the first thing we did was we did a run with just the chloroform, and then we did a run with the chloroform and the nanocrystals. Sort of, we did each one of these as well. And for the most part, they look to be very similar. At some of the peaks which the chloroform absorbed at, we had an enhanced absorption due to the nanocrystals, due to enhanced scattering. But for the most part, they agreed very well, except for over here in the lower wavelengths over here. And this is where we really see the presence of nanocrystals. And this was echoed by Dr. Matt Graham of the physics department. He said it's very probable that these are nanocrystals themselves. So we could take a look at this, and we can infer a few things. If we look at the wavelengths that they start at, we could actually back calculate the absorption curves. We could back calculate the bandgap energy, and then from the bandgap energy, we can sort of back calculate some of the size distributions. So we know that these are actually very small. It's a very small batch, 5 nanocrystals, 5 nanometer diameter nanocrystals and smaller. That's what we see from this. We also see it's very broad. I don't know if oh wow. So we see it very broad, and that comes from the size distribution. So we have a very large size distribution, and we did that on purpose because if you want to, you can get a size selection. You could get a very narrow size distribution, but that comes after you precipitate out nanocrystals. And we didn't want to precipitate them out. We wanted to use all the nanocrystals that we could. We wanted to focus on making as many detectors as possible. So that's why we have these large distributions in size. And because of that, no photoluminescent characterizations were performed. And finally, the response to radiation. So we have a polonium-210 source, which we use that emits a 5.3 MeV alpha particle. Unfortunately, the low signal-to-noise ratio made discerning signal very difficult. So there was no observable sensitivity to radiation. And this is the mock-up of the electronic setup, which I actually brought with me today. And this is a cartoon of the experimental setup that we have, that we did the testing with. So at this point, I made Class D prototypes, which is a last effort. And I purposely made them thin, because I thought that if I made them thin, I could probably show that there is a response to radiation. And due to the fact that the previous detectors were very thick, again, I wanted to sort of separate myself from the previous work by making these of the millimeter scale. So if I wanted to show that there could be a response to radiation. So I made a small reservoir made by indentation. This is actually Dr. Yang's idea. And so all of Class D detectors had a mixture of 30 milligrams of that conducting polymer. At this point, we were sort of past deadline, over budget. I probably should have been doing other things, but I ran out and got some conductive wire glue from Radio Shack. I let them cure, but unfortunately, the top contacts disconnected and they amputated, as you see right there in the picture. So none were able to be tested for response to radiation. So in conclusions, there's some successes and some challenges. So there's some small solutions: 3D printing, the digital thermometer, the conductive epoxy, the extra oil bath, the hairdryer. In prototyping, we did successfully synthesize nanocrystals and produce IV curves. But I think the results really show, if anything, that the material itself may not be, and the deposition methods may not be ready for the larger scales that I attempted to produce. Also, it's sort of expensive to verify. I think TEM is probably the best means of verification, and unfortunately, it's sort of hard to verify each batch. So in the future, better deposition methods. Right now, spin casting is the best, but perhaps maybe we could even think outside of the box. Maybe some sort of curing methods can be produced where we're not dropping things together. It's hand in hand with the synthesis methods, really. We need to create synthesis methods with short conductive capping ligands instead of the oleic acid, and maybe make a material out of a mixture of better methods in general. And in the farther future, we could take from what they're doing over there in density functional theory with their computational modeling and test for exotic shapes. We have nanorods and even nanowires here, which still have a dimension of confinement. But as you see, maybe we could leverage these longer length scales to improve charge transport. References? All right, any questions?
So, I mean, if you had resources and access to whatever fabrication how would you manufacture these? Like, clearly doing them by hand doesn't seem to be the best method, but is there a way to make these so you actually have control over the whole thing and ensure that you could do the testing that you needed to do?
Okay, so I'm going to try to answer that the best I can. The first thing I would like to talk about is I actually brought an Arduino in, and I had servo motors, and I made something that dipped and had, I could dip and use that. I didn't use that there, but what things would I like to use? Automation obviously is something that I was looking into, so that's why I brought that story up. I think I was looking at, during my off time, I was looking at sort of using E-jet printing. I think E-jet printing was sort of interesting. Maybe I would look into, if I had the resources, using some type of printing device, maybe utilizing electric field or magnetic field to help. But ultimately, I just think the whole thing is we need to look at the previous two steps. I think it's sort of outside of what I can do, and it's more dependent on the synthesis. Maybe if synthesis methods could change, maybe if we could get the chemist to put something in that we could cure. Ultimately, this may seem kind of wacky, but the best thing I would envision, if I could do anything I want, I would have a mold and make liquid nanocrystals, and then use a magnetic field, say, to align them in the preferential orientation that we get from density functional theory, align them correctly, and then maybe heat it up or have some process where by heat it starts becoming a uniform solid. And that would be sort of my dream in the future for this stuff. I hope I answered your question.